What's up? How's it going? It's Papa Bale. We're oh, let me get my sign here. My daughter got that made for me, made that for me. Dad's workshop. Heck yeah. All right. So, welcome to Dad's workshop. It's Papa Bale's Playhouse. You put a little bit of voltage in here. So I guess hitting that one over there. Let's move it back a little bit. Nice. Hey, Michael. It's Pulse Motor. Chill out, man. Three question marks. Hurry up and answer my question, crap. Man, that's not cool. Well, it's definitely not a bomb. It is not a bomb. It's just a pulse motor. So it's not a bomb. Sorry to disappoint you. Well, these 4 coils generate electricity. And these 2 coils run the motor. And that's basically it. You can take a look at some readings if you want. See? Just got a nice crisp wave right there with peaks of about 250 volts. Yeah, it's just a DC brushless motor that uses coils to generate electricity, spinning magnets by them. Magnetic induction, electric induction, not heat. It's just leaving the imprint of the north or south magnet in the copper. Just like that. That's all it really does. And we were going to look at how using different rotors and different placement of the coils would change this wave and how much electricity we get in or out. But right now we're putting in 7.5 volts parallel, so each drive coil's got 7.5 going into it. So I don't know how you want to add that up. It's 7.5 parallel, that's how I would add it up. Just a hobbyist, Michael, sorry. Just a hobbyist. Definitely not an engineer. If I was an engineer, I would say, man, you need to go back to school. Yeah, I definitely, if I want to be an engineer, I gotta put a lot of time into my education. I'd say I know quite a bit for how much I put in so far, though. I don't know. It's a YouTube education. That much I can vouch for. Alright, so I'm going to turn this up to 9. See, we're already getting some vibrations in the table. So we're going to be done with this demo in just a little bit, and we'll put the 4-magnet rotor on. Yeah, about 240, 250 volts peak to peak. And that's a crisp wave. It's not a sine wave though, because it's not made the way sine waves are supposed to be made, but it's definitely a crisp wave. I got this is mainly impulse motors. Um, but I've done some counter rotation devices. Here, let me get my latest one. Kind of more like a dreidel or a top. See, this is the stator, and it spins like a top. And then the rotor rests on top, and it's supposed to spin the other way. But because I made the stator out of copper infused PLA, it sinks. It won't counter rotate because the magnets grip the copper like they would a piece of aluminum and drag it forward. It actually kind of acts more like a brake. This is an 18-volt system or a 9-volt parallel system. Either way you hook it up, you got 2 9-volt batteries to work with. And it's supposed to, it should pick up speed. I balanced the weight pretty well. If it was made out of regular plastic, it would work probably really well. It isn't, it's not the magnet, it's not magnetism that, it's eddy currents. It's not magnetism, but I'll show you. Well, I don't know how much I'm going to be able to show you, but this aluminum disc, yeah, I need a shaft and a way to put it up next to this. But if I put it up next to these magnets, it would make it spin. It's not really magnetism, though. You're right, it's not magnetic. God, how do I demonstrate this without like having to go to a different place? A lot of my stuff is in my storage unit, so I don't know if I'm going to be able to show you. But basically, the magnets will pull it or will pull it along. Not from magnetic force either, it's eddy current. Alright, but I'm going to get the 4-magnet rotor and we're going to see how speed conquers all, basically. You see, copper is non-magnetic too, but it'll pull, and it'll definitely pull. And I thought it wouldn't, you know, I was like, but the copper has the same principle in that regard as aluminum does. And the reason I know this, and I'll get those for you too, is I made a bunch of Utrons, scalable. All right, oh, I got all the stuff here. See, you got these little shapes here called Utrons, and they fit in this rotor, or they should fit in this rotor. Go Utron, aluminum, Utron, aluminum, Utron, aluminum, like that. These little shapes are sweet, and each one of these is hollow in the middle. Copper infused PLA. You spin a permanent magnet by it fast enough, it'll start spinning in the direction that it's going because of that same principle. All right, so I'm going to turn this, I'm going to move these coils around real quick, and then we're going to turn it back on. Now we're decreasing the size of the magnets. That's one thing that's going on. Oh man, okay. So we won't go in so far. All right. This. This one, this little coil right here, man, is amazing. It's a lid square coil, and it really dominates in my mind. It's so small. But we're going to have an acceleration phase that is very short. And that's a north-south arrangement. Oh, it's so quiet, man. That is awesome. Get our AC reading. All right, so that's decent. With the cube magnets, we're getting 70, and it's north-south, north-south, 4-magnet arrangement. That's AC volts. And there's our our meter reading. Totally off the wall, man. That is crazy looking. 230. We got 8 volts in, so we got 230 on the peak to peak here. I want to see how much amps are coming out of this thing. Oh wow, look at that. It's crazy. That is a weird wave. Here, let me get it up here for you. That's awesome though. And that's 230 volt peak to peak. Very sharp wave. We're going to see if we can't get it to light up the 100 watt uh, light bulb. We'll go 9 volts in. We're drawing 100, about 100 milliamps total. Oh yeah, we were going to look at that. Alright, DC is about 500, but we're not looking at that. 275 milliamps, which is about right for all 4 of those coils. And I mean, we're probably doing 100 milliamps per power supply, so that's 200 milliamps altogether. So it's right on par, kind of, pretty much. Neat. See, what I've been trying to find a way to do is to hook these bad babies. They got spherical centers that are hollowed out. So if we can get these into this rotor and have them spin, that would be great. That'd be phenomenal. Even if I gotta like redo them to make them spin, that would be awesome. And I've never seen a schematic of the thing I'm trying to build, you see. I've only seen a picture of it. That's it. I've only seen a picture of it. And I kind of got the gist on how it runs. I've got numerous around my storage unit and here crystals that I can use. See, I'm only trying to make a tabletop sized one. I'm not trying to make a spaceship for me to ride in. I'm trying to make a little thing that sits on my table or on a desk, something like that. But granted, the idea did come from a thing called the OTCX1. And I think it would be pretty awesome if I could even get one of these Lutrons to spin. That would be like a breakthrough for me. Alright, so wow. 280, 270, 280. We're gonna up it to 12 now. Yep, that upped it to 370. That is awesome. Those peaks look wicked. Alright. I think I have a way to demonstrate how the aluminum is, how it works. I wish I had, I think I do have one of those things just for now. Sweet, I do. Awesome. Oh, it looks like I only got one of the nuts left though. Well, there's some on the table, so that's okay. That is so smooth. That is running like immensely great. It's so smooth, man. I'll get some tack readings when I put it back on, but I'm gonna like put this above that magnetic disc, or the disc with the magnets on it. Then I'm gonna rest the aluminum up there. We're gonna see how long it takes to get it to move. Great. All right, so it's not going to be magnetized, but something is definitely going to happen. I think. I mean, the magnets might not be orientated correctly, but I think they are. Here you go. Go 9 volts in. See, it's just a force, eddy currents. And if it was magnetism, it'd be a lot stronger than that. And that's awesome. I wanted to do this as part of the demonstration. So, Mike, right now I'm using eddy current and magnetism to spin an aluminum disc. Magnetism to spin the rotor on the bottom, and eddy current to spin the disc on the top. That's awesome. Let me see how fast the disc on the bottom is spinning at 9.5 volts in. Huh. It's about 1,000 RPMs. little under 1,000. And the disc is literally 2.5 inches up, and we're getting some motion. That's awesome. So we're gonna go up to 12. I'm seeing how high peak to peak we can get within a relative range of voltage in. So we're going to go to 12. But we're, let me think here, we're parallel circuits, so we're going to go 12 into both circuits. There we go. Yep, we're at 330 volts peak to peak. And our coils each have an inch air gap, so that's pretty powerful. Alright, let's try and light a light up real quick. Oh, we got gold. Awesome. It's a 100-watt LED. That's awesome. It was pretty bright too. You can hear the drag on the rotor though. We try and hook the meter back up to the same output that it was hooked up before. Yeah, all right. Now I can see what happens when we actually turn the light on. What happens? If you're gonna like spell it right at least. I mean, it's not a bomb, homie. Wow, it's just unbridled ignorance. That's all right. It's always been the same. There we go. Sorry about that. Anybody else? Yeah, you want to build a bomb, I suggest you read a book. This is not a bomb, this is a pulse motor. Fucking retarded. Oh my God. Sorry. I gotta take a minute. I'll be back later. Yeah, I'm using language I shouldn't be using. Bye now.